So also you should be able to turn your video on if you wanted to show me an answer or whatever, but yeah, let me bring up. So can you guys see this screenshot on the shared screen then? So I can try to, that's going to make it really tiny. Maybe what I'll do is I'll recopy this. Well, I'll just do it from the mouse. So it says, identify the most acidic proton in the compound. So you're given your choices A, B, C, and D. So the acidity trend that we learned, maybe I will try to do both here. So you can see the prompt and you can see me writing. So it's asking you, I'm actually going to draw these hydrogens out. So HA, HB, HC, HD. So if we sort of just be logical about this, and if you were taking a written exam, this is sort of the stuff I would expect you to write down as well. So this is CsP3, that's that hybridization of carbon. HB is equal to CsP3, HC, CsP2, HD equals CsP2. So the trend that you learned was SP is greater than SP2 is greater than SP3. So if you look at the response here, it says identify the most acidic proton. So D was chosen as the answer. But if you look here, you know, C and D are both SP2, so you really can't differentiate between them. And while this is not a trick, and the trend is that these should be more acidic than these, HB is a special case because it's allylic to the pi bond. And so what that means is when you deprotonate HB with a base, I'm just going to call it some base, you're forming a negative charge there. That negative charge can be delocalized through resonance. So there's our resonance arrow. To the other position of the alkene. So I realize that you probably can't see that. So there it is again. When you're deprotonating HB, you form this allylic anion. Through resonance, it's stabilized at the other position of the where the alkene was. So when you're talking about acidity, you're also talking about the stability of the conjugate base, because that negative charge is delocalized over two spaces. HB is the most acidic. So let me open up another one on acidity. So if you can see the question that's up there now, you have A, B, C, D, and E. Since there are only a handful of you guys here in the meeting, you obviously you see A is not the correct answer. So what do you think might be the most acidic proton? So Hannah says B. So it is B, and the reason is the following. So I'm going to shrink this down a smidge so that you can see what I'm doing here. So there's HA. HB. HC. HD. HE. And so the reason that HB is the most acidic, again, is due to resonance. So if you have some base, again, a Lewis base supplies electrons. We abstract that. We break this bond. The electrons go on that carbon. And I'm just going to abbreviate the structure so that I don't spend a lot of time redrawing stuff. So from here, I'm just going to abbreviate. So now there's your conjugate base, and then you're losing this as the conjugate acid. So that abstracts that. There's your conjugate acid. Here's your base. Now this negative charge is now delocalized through resonance. So here's your resonance arrow. You can delocalize it again. Onto the oxygen. So the more resonance forms you have for something, the more stable it is. And so that's an indicator of acidity. So here's another problem. You have a 3-carbon aldehyde propanal. You're given choices A, B, and C. We see that A is obviously not the correct answer. So what is the correct answer? And then my next question is why? So Hannah says B because it's allylic next to the double bonded oxygen. So yeah, that's correct. So HA, this carbon is sp2 hybridized. This is sp3 hybridized. This is sp3 as well. Again, the difference is the fact that when you deprotonate this, the negative charge can be delocalized onto the oxygen. So we have our base B. A base abstracts the hydrogen. The electrons end up. Right next door here. So there's negative. We're losing that conjugate acid. And then through resonance, we delocalize onto oxygen. And so remember that's good because oxygen's electronegative. It can stabilize the charge. And I believe we have one more from that group of screenshots. So we're given, let me draw this. Newman projection. So Hannah says it needs dashes and wedges. Maybe maybe Hannah wants to show her camera. Max says he could not figure out where to put them. Maybe Hannah, if you have an answer you want to share, hopefully everyone would be able to see if you shared it. Again, I'm not sure how all this stuff in Teams works so much. So Hannah says it doesn't matter. It kind of does matter, because you can end up with two very different answers if you don't put them. Are you guys able to share your cameras or no? So maybe give me a second and I'll make a little molecule here. So if you got some funds, I prefer this model kit, HGS Stereochemistry Model Kit. They don't make this specific one anymore, but it's similar enough. So I'm gonna throw together a couple carbons here. So as we saw in Mac's answer, the ring size is 5, right?
Yeah, and to count that, don't we use the two carbons from the middle of the Newman projection, the one in the front, the one in the back, and then the ones to the right side of it where it's 1, 2, 3. So that's a 5-ring structure, and then there's 2 methane groups off of it.
Yes. So bear with me a second here. All right, I was just figuring out these hydrogens. So what I'm holding now is the bond that you're looking down in the Newman projection. So again, in a Newman projection, you're always looking down a single bond. So if you count, the front carbon is 1, the back carbon is 2, then you have 3, 4, 5. So what you can do from there is just draw a 5-membered ring, number it 1, 2, 3, 4, 5. So what you need to understand, the Newman projection's use is, so this right here is what I'm holding in my hand. So see, this methyl group up is this methyl group. Then behind is that methyl group. So all a Newman projection is you're looking at from a different angle or a different perspective. So to convert it to this, all I'm going to do is rotate 90 degrees now like that. And so the wedges and the dashes, so this front carbon, that methyl group's going to be up. So that needs to be a wedge. The hydrogen is down. You can see the relationship between the methyl and the methyl is 180, right? So that means this methyl on the back carbon 2 has to be down. And then the hydrogen has to be up. So there's your wedges and dashes. So again, I'm holding carbon 4. And if you're looking at the Newman projection, you're looking down the bond axis. So the front carbon, if I rotate now, the front carbon is up and the back carbon is down. So it's hard to get all this stuff in the frame, but again, the Newman is just a matter of your perspective. So Hannah had a question earlier in the chat, how to tell most stable chair conformations. Do you have a specific one you want to look over, or I can just open up the workbook?
I had a few that were on Orion, but I didn't screenshot them. I have them written down. And maybe I guess I could show you my paper. I can type it out.
Yeah, I mean, are you guys able to show your camera or not? And is it just like a Teams thing, or are you just?
Can you see me? My camera's on right now.
I cannot. Let me. I can see now. Can everyone else see?
I had quite a few of these questions, and I know the general rules for stair or for chair conformations are that the equatorial positions are most stable, and then after that, your larger group should be on the equatorial position to be most stable. But I didn't know how to like use those rules to like problem solving strategies. So I missed like 3. Well, there were 3 questions. I'll type them all out if you give me a minute to type it, or I could say it out loud. Whichever one you prefer.
Maybe just say it first.
Okay. It asked which the substituent in the most stable conformation of 1 tert butyl 1 methyl cyclohexane. So ask for like both substituents on it, and like where would they be in the most stable?
So this is it. 1 tert butyl, 1 methyl cyclohexane.
Mm-hmm. I have 3. They're different things.
So let's go through this one first, so everyone can sort of see what the issues are. So again, part of the skill of what you're doing in this class is to take a name and convert it to a structure. So first we're going to convert it to the bond line, and then we'll convert it to the chair. So we see the parent here is hexane. It's in a ring, so cyclohexane. And so right here, that's the parent, and everything in front of it are substituents. So let's go ahead and draw a cyclohexane. So there it is. Let's number it. 1, 2, 3, 4, 5, 6. So this is saying at the 1 position there's a tert-butyl group. So this is tert-butyl. So what does this mean? Butyl is 4, right? That's a 4-carbon unit. Tert means it's tertiary. So it's saying, so there's your 1, 2, 3, 4. It's saying that the connection is to the tertiary carbon. So there's 1 tert-butyl, that's that substituent. Then we have a 1-carbon unit, 1 methyl. So there is that molecule. We've converted the name to the structure. Now what you have to realize is that we are not flat. We are 3-dimensional things. So cyclohexane is not flat. And the reason that is important is because the substituents will occupy different positions, either equatorial or axial. So let me make another model of this just so we have a 3D thing to look at, and then we'll draw it out. So the first things first is knowing that we're not flat, and so for cyclohexanes, the conformation that we typically start drawing is called a chair. So that's a chair, and I'm going to do sort of a slight, not a cheap trick, but I'm going to start the numbering at this carbon right here. It's fine. I'll show you. We can start numbering it any way, really. So if I was transforming this to this exactly, I would put the 1 right there, but it doesn't really matter. So when you put these substituents in, what this question is asking you for is which substituent is axial, which is equatorial. So Hannah says they can't both be equatorial because they are on the same carbon. One has to be axial, one has to be equatorial. So that is correct. So in the chair, this carbon 1 here, you have 2 substituents, right? One of those is axial. It's straight up and down. The other is equatorial, axial equatorial. Hannah later goes on to say the tert-butyl would be equatorial. And I think she meant to say the methyl would be axial, yes. So if you look at the size of this thing, and I've made a model of it. So here's our chair. So you can sort of see the chair. I'm holding the tert-butyl group with my right hand, and then here is the methyl group. The tert-butyl group is very big, and basically we want to put it equatorial versus the methyl group, which is axial, for the following reason. So the other top, so top, bottom, the other axial bonds are here, and those are both hydrogens. we want to minimize this interaction between all these axial bonds on the top and the bottom. So if we were to do sort of a chair flip, so this is a chair flip. We want to minimize this large group banging into these other groups that are also axial. So what you're doing is you're comparing sizes. The methyl group is small. Tert-butyl group is large. The gist of this exercise is you put the large group equatorial, the small group axial. So in terms of both of these, the conformation to the left would be preferred. So we would draw a large arrow this way, small arrow that way. So you'll notice a lot of these problems have a tert-butyl group. And so what that is really doing is it's conformationally locking the tert-butyl group into the equatorial position. So let's convert this to a bond line. So first things first, draw your cyclohexane, throw some numbers on it. One of the best skills you can develop in this course is numbering your carbon backbone. When we start learning reactions, this is going to be very important. So it says trans 1 tert-butyl 3-methyl cyclohexane. So for now, let's just ignore the trans. Let's just put the substituents in. So at the 1 position, we have tert-butyl. For the 3 position, we have methyl. So now that's our first approximation. Let's do our second approximation where we actually consider what trans means. So if I draw the tert-butyl group like this, how should I then represent the methyl group at position 3 if we want it to be trans? Should I put a wedge or a dash here? We're going to put a dash. And so now we have to take this and convert it to a chair. So I'm going to put the 1 here, the 2 there, 3, 4, 5, 6. We know that tert-butyl is large, so we want to make it equatorial. So converting this to this group is up. So if at position 1 here, it's going to be equatorial, it's going to be up. Does everyone see that? Your eyeball is looking this way, that group is up. When you look at the chair, you're sort of looking side on. So if the 1 position up is equatorial, the methyl group at position 3 should be what? If it's down, should it be equatorial or axial to conserve the trans relationship? So Hannah says axial, that's correct. So see how this is up, up, this is down, up, down. Now, what you have to be cognizant of is that as you move from carbons 1 to 2 to 3 to 4 to 5 to 6, the axial equatorial relationships change. So you really have to do it on a per case basis. It's not good to memorize things so much. So Hannah, I think you said you had a third one. Let's go ahead and so let's do Mac's question, then we'll get to Hannah's next one. So he says, if it were cis, they would both be equatorial. So this is the trans. Let's do the cis 1,3. So this is equatorial, it's up. This has to be up as well. So there's cis. We're at position 3. That's up. We need this up, so that's also equatorial. So yeah, they're both equatorial. Let me show you something so that you see I'm not bullshitting you, and you sort of see that there's no tricks being played here. So I'm going to start the numbering, not at that carbon, but I'm going to start the numbering here. 1, 2, 3, 4, 5, 6. We said the tert-butyl group is at position 1 and it's up. So in this representation of a chair, at the 1 position, is the tert-butyl equatorial or axial? So it's axial. So now if in the cis relationship at the 3 position, the methyl group should be equatorial or axial. So yeah, it has to be axial because they're cis, right? They're both up. So what is the difference between this and this? I mean, all I really did was just change the numbering. So Hannah says it's the stability. So yeah, that's exactly right. The relationship between these two things, again, they are conformers, conformational isomers. So this conformer is less stable because you're putting this group axial. So what it does is then it does a ring flip. So it flips and you get this. And I'm not pulling any tricks on you. The difference between these is just the matter of the perspective at which your eye is seeing it. And so that's where these model kits really come into play and can help you. So for example, before we get to Hannah's question, you've probably seen in the homeworks and Orions about Newman projections of chairs. So here's sort of the regular cyclohexane, then when we rotate it, then look at that. Now you're looking at a double barrel Newman projection. You have a Newman projection here. and then you have a Newman projection here. So all it is a rotation. It's just nothing changes. It's just how your eye sees it. So let's go ahead and do trans 1-tert-butyl 2-methylcyclohexane. So again, bada bing, bada boom, number it. And I'm not going to like wax poetic here, but if I were to give you guys a face-to-face exam and we had a normal class, a normal situation, I find a lot of students do not write down their thoughts. It's good to go through this. You try to do too much in your head, and you lose track of things. So we wrote our cyclohexane down. We numbered it. The 1 position we want tert-butyl. The 2 position we want methyl. So that's our first approximation. Now we want to put the trans in. So now we want to take that, convert it to a chair. So maybe I'm going to do this. I'll put the 1 here, the 2 here, the 3 here, the 4 there, the 5 there, the 6. So the tert-butyl group at position 1 should be what? Equatorial or axial? So it's up. On this carbon 1, the up bond is equatorial. Then the methyl group at position 2 should be what? Equatorial or axial? So yeah, it has to be equatorial because this group is up, this group has to be down to be trans. So that's what I mean by you know, the relationships between the carbons as you move. So let me show you that so we can, if I draw, I'm going to go in and draw all the equatorial relationships first. If I start here, this carbon has 2 substituents. The equatorial one here has to be up. Since this carbon is up, the equatorial one here has to be down. This carbon is down, the equatorial relationship has to be up. This carbon's up, the equatorial relationship is down. This carbon's down, equatorial is up. This carbon's up, equatorial is down. So notice how they flip, up, down, up, down, up, down. Now if we put the axial groups in, and I start here, this carbon is down, the axial group is down. This carbon's up, the axial group is up. This is down. Look at this artistry. I made a little space. I'm giving you some perspective here. I'm the Bob Ross of cyclohexanes. This axial is up. This axial is down. This axial is up. Make it a little bit bolder. Make a little happy little axial bond here. So notice now on the top face, the top, we have 1, 2, 3, 3 axials. On the bottom, we have 1, 2, 3 axials. Then along the equator, you have 1, 2, 3 up, 1, 2, 3 down. So even though it's a pretty simple molecule, cyclohexane, when you see this written, your mind should think of this in reality. So let's ask. Do you guys have questions? I have someone else emailed some. I can do those, or if you guys have questions, I can answer those.
Can we talk about assigning R and S, especially when the H is not on the dash?
So assigning R and S. Let me flip through the workbook, see if there's some appropriate problems we can do in there. So let's do some of these from the workbook, and it's sort of generic, so this might not be the most useful thing to you guys, but we'll go through it anyway. This is page 111, chapter 7, section 2, determining configuration of a chiral center, starting at problem 727. So this is conceptually looking at scenarios with your priority groups 1, 2, 3, and 4 in different arrangements. So you're not necessarily given a specific element, but this, I think, sort of answers or gets to what you're asking, and then we can look at some specific ones. So for 27, the lowest priority group is towards you. So whatever you determine in terms of your rotation, you have to flip to the other configuration. So what do you think 27 should be? Maybe just type it in the chat. So again, there might be students responding super fast. I still encourage you to do it yourself and then respond in the chat. So yeah, 4 is towards you, and when you connect 1, 2, and 3, you're initially going clockwise, which would be R, but since 4 is towards you, you have to flip it to make it S. If you have really good visualization skills, you can almost picture your eyeball behind the page of this paper where 4 would be the lowest priority group pointing away from you. And then you would get the correct answer is S. It's really takes some mental gymnastics to do that. So what about 28? Now the lowest priority group is in the plane of the paper. So yeah, this one's R. And again, this one does take a little bit of mental gymnastics, because if you want this to be behind, your eyeball has to be here. And when you do that, the 1 is sort of up, then you're coming down to the 2 to the 3, so you're going clockwise, so that's R. So what about 29, where 4 is in the plane of the paper again, the lowest priority group? So if you wanted to put that back, your eyeball would need to be over here, looking from that perspective in the plane of the paper. Yeah, so this should be S. We're going 1 to 2 to 3. That's counterclockwise S. Let's see if we can find some actual molecules here. So your question was basically when hydrogen is not the lowest priority group, right?
Right. And I actually have an example, but it's like in the chair thing. I don't know if you can see it or not. The first one, this one right here.
Okay, yeah, let me just copy that down real quick. We have H, and then, so yeah, that looks like it right there.
Yes.
Okay, so our collective goal is to understand assigning R and S to those chirality centers. So first, let me ask, how many chirality centers do you see in the molecule? So yeah, there's 2. So I've taken the chair and I've reconverted it back to the bond line, which may be a little bit easier to determine the R or S configuration. So let's look at this one right here first. So we see that this one has a hydrogen on it. So that's going to be the lowest priority group. Then you have carbon, carbon, carbon. This has 3 hydrogens. These both have 2. So this has to be the 3rd priority. Battle of which one of these wins. So if this carbon and this carbon, say top, we'll keep it easy, top and bottom, which one gets the higher priority? The top one or the bottom one, and why? So Hannah says the bottom one. So what we're doing, these both have 2 hydrogens, so those cancel each other out really. So we move out, we go to carbon, and we have carbon, and so we compare those. 2 hydrogens, 1 carbon, 2 carbons, 1 hydrogen. So yeah, the bottom one is going to win. So this should be 1, and then this should be 2. So knowing that, what should this stereocenter be? With the lowest priority group away from you. So yeah, this should be S. Now why don't you guys try doing this next one before I work through it? Type your response in the chat, and then we'll see if there's a consensus. So we know that the hydrogen's the lowest priority group. It's pointing towards you now, so that's important. Now, the challenging thing about this is carbon, carbon, carbon. So you have to go out. Carbon, carbon, carbon. So we can sort of see as we move out that this part here has to be lower priority than the other 2. So that has to be 3. Because you're hitting a carbon with 3 hydrogens. When we go out here, we have carbon with 2 hydrogens. We go out here, we have carbon with 1 hydrogen. So this has to be higher. So 1, 2. Now we're going clockwise, which would be R, but since the lowest priority group is towards us, we flip it to make it S. Just want to remind myself to do these other problems that a student had emailed about. Let's do these problems on the screen real quick, and then we can get back to some more configurations. So a student had asked about this compound, about identify the 2 compounds below that have the same parent. And so what can be challenging about these is that I was working with a student earlier today, and sort of my diagnosis of this sort of problem is the following. So yeah, when you look at them, you just count the parent chain. But so Hannah, the issue is, sort of in my opinion, is you have to, the parent chain might not be obvious to you. So you can't, and I can't think of any way else of saying this, is you can't just quit after you do it once. And what do I mean by that? So if you're a little green person and you're standing on the backbone of this molecule, you're really tiny, your atomic scale. And it's like those like maze books, you know what I mean? You're starting here, you go boom, and then what if you go this way? You only count 3. Well, that's not, you can't stop there because you have to evaluate all these other routes. Well, you go here. I'm obviously not stopping there because I see as a person on this backbone, I see another carbon. But what if I go there? Well, hey, is that the longest chain? Well, not really, because I hit here a branching point. I can go this way. And so if I count these, that's 3, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. Well, this is still a branching point. I want to explore. I'm Indiana Jones. 7, there's 8. Well, hey, there's still a trail here. So 1, 2, 3, 4, 5, 6. What am I? I can't count. 1, 2, 3, 4, 5, 6, 7. This should be 7. I go here, that's 7. Whoop, there's 8. So the sort of issue is, as a student, what I showed you is just sort of one way. Let me just redraw this so you can see the point I'm trying to make in very winded terms. As a student, you want to focus your eye, in my opinion, sort of either to the left or the right, and not start at some random place. So say I want to start here, but I can sort of already see that, you know, this carbon isn't going to be included in the longest chain. So if I start here and go this way, then I'm not taking any branching routes at this point because I know they're only leading to a single group, a single methyl group. I've walked, I'm a little red person now, and I've walked along this route. So I guess the point I'm trying to make is you don't want your eyeball flittering around and starting in some random spot that you know is not going to include the longest chain. You just need to like train yourself, as Hannah said, you know, you want to find the parent, but you want to sort of be logical at where you start. So in where my mouse is on the screen now, you know, I can sort of see by comparison to the second structure compared to the top has one more carbon because I see 1, 2, 3, 4, 5, 6, 7, 8, and then 9. Then I see the third one. Well, the third one is sort of, it resembles the top one, but they sort of clipped this group off and moved it over here. Then this fourth one, they're sort of clipping 2 groups off, so it has a shorter chain. Again, it's how you train your eyes to look at these things and consider multiple routes. So Aiden, we'll get to your question after we sort of review this next acidity question. Predict which side of the reaction is favored under equilibrium conditions, and provide a brief explanation. So the choice A is not correct. What do you think is the correct choice for this? And you can answer in the chat. So the way the prompts are written here, they're sort of putting distractors in a lot of them, so you can figure out that B is the correct, B as in boy is the correct choice. But the logical way you look at this is you're looking, again, for organic chemistry. Even though we're looking at acid-base reactions, a lot of organic chemistry is focusing on the acids, because we then use pKa values, as Hannah says in the chat. This is what we quantitate with. So on each side, you're looking at the acid. You have this acid, and you have this acid. Generally speaking, what is the pKa of an alcohol? So the pKa of a typical alcohol, we're going to say, is about 15. The pKa of ammonia, does anyone know offhand? So yeah, about 40. Between 15 and 40, which one's weaker? Do you understand what those numbers mean? When you compare that, so again, we're only right now focusing on the acids because it's going to help us answer the question about how this arrow is drawn. So 40 is the weaker one. So that means, because this is weaker, the equilibrium favors this side. So the reaction is favored in the forward. That's what that means, the forward direction, this way. That gives you choices B and D. And then you just use your logic. Oxygen is more electronegative than nitrogen. That is true. So at that point, you can't eliminate B or D because they both have the same wording, right? What you do eliminate then, it says C is a weaker base than B. Yes. This is component C. This is the weaker side. This is the weaker base than this. So yes, Hannah, it is this is the weaker side. And so that language is what choice B as in boy, is saying. So choice B is correct. So Aiden asked about, why is phenol more acidic? So this is ethanol. This is phenol. So Aiden, what is the pKa of phenol? We already said ethanol is about 16, 15, 16. So we compare these numbers, 16 versus 10. Again, it's important to understand the difference is not 6, it's 10 to the 6. Remember, the pKa, the p is a log function. So log is 10. 16 minus 10, that's 10 to the 6. This is 10 to the 6 times more acidic. So can you think of a reason why that is? What I want you to do is draw the reaction of each of these with a base. Draw the conjugate base that is formed. after the hydrogen is deprotonated. It's not induction. It's something else. So again, when you're talking about an increase in acidity, you have to look at the conjugate base and what factors stabilize the charge on the conjugate base. Because look what you're doing. This is OH and this is OH. Both of these are forming O minus, O minus. What stabilizes this O minus versus that one? So see if you can draw it out first before I draw it. So Aiden's hedging his bets with the question mark. I appreciate the answering a question with a question, sort of to cover all sides. So again, we're treating both of these with some base B. So now look, we said we have OH, we have OH, we're treating with a base, we're forming the same conjugate acid. Now what stabilizes this versus this? They're both O minus, right? This negative charge is only on that oxygen. This negative charge is stabilized through resonance. So the more you can delocalize that negative charge, the more stable this is. So when you're talking about acidity, you have to consider a lot of things. So resonance is one of the primary reasons why phenol is more acidic than ethanol. So maybe I'll take one more question. So why is water more acidic than ethanol? I would say that's sort of, you're getting really into really specific things. I don't know that that's really important to answer right now. You know, if you're comparing 15.7 versus 16, yeah, there's a slight increase in acidity. But I don't know if getting into that sort of detail is important for the scope of this course. So let me just say, as I posted in Canvas, you know, you do not have to use the Respondus lockdown browser. You just click that link and it should take you right into Wiley Plus. You have the distribution of questions as shown in Canvas. So there's 3 difficulty levels: easy, medium, difficult. From chapters 3, 4, and 5, you're getting 8 questions from chapter 3, 8 from chapter 4, and 9 from chapter 5. So that's your 25. You're getting 4 points per question for a total of 100 points. You get you get 2 attempts. If you don't get it right on your first attempt, you get another, but your maximum score can only then be 2 points. You have 90 total minutes to do the exam once you start it within the 24-hour period. If you have any technical difficulties, you know, my advice, the first thing you should do, even before you start the exam, is clear your browser history, shut down your browser, restart your computer, and then just start fresh. If that doesn't work, then reach out to Wiley Plus for immediate help. Any further questions before we wrap up the office hour here? Again, I don't see any in the chat. You know, I'll check my email a couple more times tonight. If you have a question, you can shoot me an email. I'll respond with that. If you have any difficulties tomorrow, again, I would say reach out to Wiley Plus first. But let me know, and I'll try to do what I can. Other than that, I'm going to go ahead and stop the recording and